Earth is the only reference, and the earliest sense of space comes from how the sky behaves above a fixed ground. Across daylight, the sun rises from one horizon and sets on the other, returning again after a single turn of the sky. Across night, bright points hold their relative patterns, while the whole canopy seems to rotate. Some stars never set circling a point that stays nearly still, while others rise and fall on arcs, whose height depends on where the observer stands on Earth. Long before any instrument can separate distance from brightness, this regular motion builds a first structure, Earth below, sky above, and a repeating schedule that can be trusted. Time is measured by shadow length, by the return of constellations, by the moon's cycle from thin crescent to full disk and back. Space at this stage is not vast or small. It is simply the container of motion, and the most dependable facts are angles, directions, and repeated sequences. The first outer region of the topic is therefore not deep space, but the visible dome itself, treated as a surface of points whose positions can be recorded. When careful watchers mark where the sun rises on the horizon through the year, they see it shift northward and southward, reaching extremes and returning. This becomes the year. When they track the length of the day, they find it changes with the seasons. When they note the moon's path, they see it stays close to a band of sky that the sun also follows, the ecliptic, even if the word is not yet used. The planets, the wanderers, follow the same broad band, but drift against the background of stars, sometimes slowing, stopping, and reversing for a time. The whole display is a map of angles, and this is the only kind of measurement available at first. Yet angles can carry scale because geometry does not require a ruler if the goal is to compare shapes and establish relative size. A key move in early astronomy is to treat Earth not as an isolated floor, but as part of the geometry of the sky. The horizon is local, and its shape depends on Earth's curvature. The changing height of the pole star with travel north or south reveals that the observer's position on Earth changes the apparent sky in a systematic way. When the same star sits higher above the northern horizon for a northern traveler than for a southern traveler, the simplest explanation is that Earth is curved and the observer stands on a different part of it. From there, the idea that Earth is a sphere becomes a practical tool rather than a belief. A sphere has a circumference, and if that circumference can be estimated, the first absolute scale enters human thought, a size for the world itself. The method is based on sunlight and shadow. If the sun is far enough away that its rays arrive nearly parallel across a wide region, then two vertical sticks set far apart will cast shadows with different angles at the same moment. Measuring those angles and knowing the distance between the sticks allows the circumference of Earth to be inferred. The result is not perfect, yet it is a leap in kind. Earth is no longer just the ground underfoot. It is a globe with a measurable size in kilometers. With Earth's size in hand, the sky can be approached with a new question. If Earth is large, what must the sky be for the sun and moon to appear as they do, and for shadows to behave as they do? Here the outer region remains the realm of appearances, but the work shifts from recording patterns to linking them to physical size. The moon's disk spans a certain angle, roughly the width of a fingernail held at arm's length. The sun spans nearly the same angle, a coincidence that allows eclipses. An object's angular size can be produced by a small object nearby or a large object far away. Without distance, the size cannot be known. But there are moments when distance becomes accessible through motion. A lunar eclipse, when the moon passes into Earth's shadow, offers a picture of Earth's shadow projected into space. The shadow has a curved edge supporting Earth's spherical form, and its width relative to the moon's disk provides a way to compare sizes. From repeated eclipses, a rough estimate emerges: Earth is a few times wider than the moon. If Earth's diameter is known even approximately, then the moon's diameter can be estimated. The next step is to estimate how far away the moon must be to appear with its observed angular size. Geometry again supplies the link. A disk of a given diameter will subtend a certain angle at a certain distance. Using Earth's size as the starting scale, the moon's distance becomes expressible in Earth diameters and then in kilometers. This is still within the near sky, but it is the first time a human measurement reaches beyond Earth's surface in an absolute way. The moon becomes a real object in space with a measurable separation, and the idea of up there changes into a distance that can be written down. Even so, the sense of vastness does not arrive all at once. The moon is far, but the number is not beyond comprehension. It can be compared to journeys on Earth, even if those journeys take lifetimes. The sun, however, immediately strains the early scale. If the sun is not a small lamp close by, then its behavior suggests a far more distant body. Its rays are almost parallel across wide stretches of Earth, as implied by the shadow method for Earth's circumference. Parallel rays imply a source so distant that the difference in direction across Earth is tiny. This sets a lower bound on the sun's distance. And once a lower bound exists, the sun's true size begins to grow in the imagination, because the sun's angular size remains fixed. A greater distance implies a larger diameter. The sun's heat and brightness also resist the idea of a small nearby object. Yet in the earliest stages, direct measurement of the sun's distance remains beyond reach, and the best that can be done is to assemble constraints. The sun is far enough for its rays to be nearly parallel, far enough that Earth's shadow in a lunar eclipse has the expected shape, and consistent enough in daily path to support the geometry of a distant source. This is still the outermost layer of the story, where the sky is observed as a dome, and only the nearest bodies begin to gain depth. The key transformation is methodological. Space becomes something that can be measured, not merely admired. The tools are simple sticks, shadows, angles, and careful timing. The mental shift is that a number can stand in for the unknown, and that repeated observation can refine that number. With this shift, the heavens begin to lose their old role as a fixed ceiling. They become a region with layers: the nearby layer of the moon, the brighter and more distant layer of the sun, and beyond them a surface of stars that still seems unreachable. At this stage, stars remain points with no measurable distance. Their lack of apparent shift against one another, even as earthbound observers move across continents, suggests they are either extremely far away or attached to an immense sphere that turns around Earth. The first hint of true vastness is contained in that stubborn steadiness. If the stars were close, travel north or south would noticeably rearrange the constellations. Instead, the patterns hold. The same belt of Orion appears with the same spacing. The same curve of the Big Dipper keeps its shape. This implies distance beyond the scale of Earth's radius, beyond the scale of the Moon's orbit, and beyond any everyday measure. Still, the implication is indirect. Vastness is not yet felt as a measured number, but as an absence of change. There is also the steady dimness of most stars compared with the Sun. If a star is a distant sun, then its faintness implies an enormous separation. But this is not yet established, and the language of distant sun is not yet available as a scientific statement. In the outer region of the topic, the sky remains a field of lights whose true nature is unknown. What is known is how they move and how they do not move. The planets, by contrast, do move, and their wandering introduces a new kind of depth. Their shift in position from night to night sets them apart from the star background. Their occasional reversal, the retrograde motion, shows that simple circular motion around Earth is an incomplete description unless complicated layers are added. The effort to account for these motions pushes geometry further, and with it, the ambition to map not only the sky's surface, but the spatial arrangement that could produce the observed paths. Yet Section 1 stays before that deeper rearrangement. It remains with Earth as the only grounded scale and the near sky as the first extension outward. In this frame, the most important realization is not yet that space is too vast, but that it is real, continuous, and measurable in principle. A human on Earth learns that a shadow angle at noon can be turned into the size of the world. From that, a lunar eclipse can be turned into the size and distance of the moon. From that, the sun's parallel rays can be turned into a statement that the sun is distant and large. Each step keeps the observer on Earth and uses Earth as the base unit. The sky stops being a painted surface and becomes a layered place. The feeling is calm and procedural. Observation, geometry, repetition. The vastness of space is still outside the numbers, waiting in the unmeasured distance to the stars. But the foundation is laid. If angles can yield the moon's distance, then angles might someday yield the stars. For now, the stars remain fixed in pattern, and that fixity is the quiet sign of a greater scale not yet reached. With Earth measured as a globe, and the moon established as a nearby body with a real distance, the next outer region is the near neighborhood of Earth, where distance can be extracted from motion when the geometry is favorable. The guiding idea is simple. If two observers look at the same object from different places, the object appears against a slightly different background. That shift is parallax, and it turns separation on Earth into a measuring baseline. The baseline can be the distance between two cities or the width of Earth itself if observations are timed across a day. The sky supplies objects that are close enough for the shift to be detectable, and in practice the moon is the first. When the moon is observed from widely separated points at the same time, its position against the star background is not identical. The difference is small, but it is measurable as an angle. If the baseline between the observers is known in kilometers, then the moon's distance can be calculated from the angle. The procedure relies on careful timing, so both observers record the moon against the same star field, and it relies on accurate knowledge of each observer's latitude and longitude, so the baseline is correctly stated. Even when early measurements are rough, the outcome is stable. The moon is hundreds of thousands of kilometers away, not a small lamp in the near air. Once the moon's distance is established by parallax, the earlier eclipse-based comparisons gain firmer footing, and a consistent near-Earth scale emerges. Earth-Moon and the space between them become the first measured system beyond the ground. The next question concerns the Sun, and here the difficulty increases. The Sun is so far away that parallax from points on Earth is extremely small, far smaller than for the Moon. Yet the Sun's distance matters because it acts as the yardstick for the entire planetary system. If the spacing of planets can be known in relative terms, then one absolute measure can convert the whole layout into kilometers. Early models can infer relative distances by studying the apparent motion of planets, especially the relationship between their periods and their maximum angles away from the Sun in the sky. For the inner planets, Mercury and Venus, the greatest elongation, the maximum angular separation from the Sun, gives a geometric constraint on their orbits if the orbits are assumed to be roughly circular. For the outer planets, their changing brightness and their retrograde loops can be explained more simply when Earth is treated as moving. These patterns, once understood, yield relative orbit sizes. But relative sizes still do not tell how large the system truly is. A scale must be attached. The outer region of this section therefore stays with techniques that tie sunlight and planetary motion to measurable baselines. One route is the rare alignment called a transit, when an inner planet passes directly across the face of the Sun. During a transit of Venus observers in different parts of Earth, see Venus trace slightly different paths across the solar disk, because each observer views the alignment from a slightly different direction. The difference in track position and the difference in transit timing encode parallax at the scale of Earth's radius projected onto the Sun's distance. If the geometry is modeled correctly, this yields the distance from Earth to the Sun. The method is demanding. It requires accurate clocks, careful observation of the moments Venus touches the edge of the Sun's disk, and coordination across continents. It also suffers from practical limits. The edge of the Sun is not a sharp line through a telescope, and atmospheric turbulence blurs it. Venus itself has an atmosphere that produces effects at the limb. These details introduce uncertainty. Even so, repeated transits observed over centuries provide increasingly reliable estimates, and the key outcome is a number large enough to reset intuition. Earth is not just a few moon distances from the Sun. It is separated by tens of millions, then more accurately, by around 150 million kilometers. This distance, called the astronomical unit, becomes the foundational measure of planetary space. Another route used as instruments improve is to measure the distance to planets directly using radar. A powerful radio signal is sent toward Venus or another planet, and the echo is received back on Earth. The time delay multiplied by the speed of light gives a direct distance in kilometers. This is a much later development, but it reveals the same truth with less dependence on optical ambiguity. It also ties the solar system's scale to the measured speed of light, a physical constant. In the period before radar, the astronomical unit is refined through many approaches, including planetary observations, perturbations in orbits, and increasingly precise timing. Regardless of method, once the Earth-Sun distance is accepted, the familiar night sky changes character. The Sun is no longer a light that moves across a dome. It is a star-like body far away, and Earth is one planet among others moving around it. Yet the most important consequence for the theme of vastness is what happens next, and it begins quietly in the near region. With the astronomical unit established, the distances to other planets can be stated in kilometers. The numbers are larger than the Earth-Moon distance by orders of magnitude. Mars, at closest approach, lies tens of millions of kilometers away. Jupiter lies hundreds of millions. Saturn lies more still. Even these distances remain within the solar system, but they create a sense of enlargement. The scale of human travel becomes irrelevant. A journey to the Moon is already difficult. A journey to Mars is far beyond ordinary thinking. And the outer planets are not just far but remote in a way that makes them functionally unreachable for long periods of history. Still, this is not yet too vast in the strongest sense, because the solar system remains a bounded system with a central sun. It is large, yet it can be mapped. Distances can be written, and the same geometry that measured the Moon can, with patience, measure the planets. The turn toward true vastness comes when this new yardstick is aimed outward toward the stars. Before that, the solar system itself must be understood as a real three-dimensional arrangement. This understanding grows from the same measurements. The phases of Venus show that it orbits the Sun. The moons of Jupiter show that not everything circles Earth. The changing apparent size of Mars during close approaches shows that distance within the system is variable and measurable. These facts support a model where Earth moves. In such a model, Earth's orbit around the Sun provides a baseline vastly larger than any baseline on Earth's surface. The diameter of Earth's orbit is 2 astronomical units, hundreds of millions of kilometers. With such a baseline, parallax might be detectable even for stars, but only if stars are not unimaginably far away. The attempt to detect stellar parallax becomes a test of scale. Observers look for a tiny annual shift in a star's position relative to more distant stars as Earth moves from one side of its orbit to the other. If the shift is found, the star's distance can be calculated in astronomical units and then in kilometers. If no shift is found, then the stars must be farther still so far that even the enormous baseline of Earth's orbit is insufficient to create a noticeable angle with available instruments. For a long time, no parallax is detected, and this absence is itself a measurement. It implies that the sphere of stars, if it is a sphere, is not a close shell. It is beyond the reach of early precision. This is the moment in the near region where human scale begins to fail. The solar system has become measurable, but the stars remain fixed. The contrast between the measurable planets and the unmeasurable stars becomes sharp. Planets wander and show parallax when observed from different locations. The Moon shifts clearly. The Sun's parallax is tiny, but can be teased out with rare events and coordinated observation. The stars show none, and the best instruments still see them as points anchored in place. The implication is not expressed as drama. It is a steady inference. If Earth's orbit is as large as the astronomical unit demands, and if stars still do not shift over the year, then their distance must be enormous compared with the solar system. The stars must lie at least many thousands of astronomical units away, and in reality, far more. In this second section, the story stays with methods and with the near-to-near-far boundary. It shows how humanity builds the first long ruler, the astronomical unit, from geometry and timing. It shows how that ruler expands the map of the solar system into kilometers. And it shows how the moment that ruler is turned toward the stars, it meets silence, no measurable shift. The sky's outer layer, the star field, remains beyond direct reach. Vastness begins here as a measured absence, a failure of parallax, not as a defeat, but as evidence that the next region outward is larger than expected, with the astronomical unit serving as the first reliable yardstick beyond Earth. The next outer region is the solar system itself, understood as a physical system, with a central sun and planets arranged by distance period and motion. The critical change is that the sky is no longer treated as a dome carrying moving lights. Instead, the observed paths of planets are treated as projections of real orbits through space. The evidence begins in the simplest observations that instruments make clear. Venus shows phases from a thin crescent to a fuller disk in a sequence that matches an orbit around the Sun, rather than a motion around Earth. Mercury behaves similarly, though it is harder to observe, because it stays close to the Sun in the sky. Mars, Jupiter, and Saturn display retrograde motion that becomes a natural consequence of Earth passing them on an inner track. The retrograde loops are not caused by mysterious reversals in the planet's own movement, but by changes in viewing angle as Earth and the planet move at different speeds. When this is accepted, the solar system's geometry becomes coherent. Each planet's period, the time it takes to return to the same position, relative to the Sun, is linked to its distance from the Sun. The closer planets move faster, completing their circuits more quickly. The farther planets move more slowly. This relationship, stated in everyday terms, expresses a deeper regularity. Gravity binds the system, and the Sun's pull governs the overall pattern. The outer region here is not the farthest reaches of the universe, but the structured neighborhood extending outward from the Sun to the outer planets, still within reach of a single consistent physical explanation. Once a Sun-centered system is in place, relative distances between orbits can be determined with observation and geometry. For inner planets, their maximum angular separation from the Sun sets a constraint on the size of their orbits compared with Earth's orbit. For outer planets, the timing of oppositions when a planet is opposite the Sun in the sky and closest to Earth, and the size and speed of retrograde arcs provide information about the ratio of orbital radii. These methods do not require knowing the solar system's absolute size at first. They build a map in astronomical units Mercury at a fraction of an astronomical unit. Venus closer than Earth, Mars, farther Jupiter, far beyond Saturn, farther still, and later Uranus and Neptune at greater distances. When the astronomical unit is assigned a value in kilometers, the whole map expands into numbers that can be written and compared. This is where the solar system begins to feel large, not by metaphor, but by conversion into travel times at known speeds. Even the fastest winds on Earth, measured in kilometers per hour, would take years to cross the gap to nearby planets. The scale of the system is many orders larger than the scale of continents and oceans, yet it remains finite and describable. Within this region, the Sun becomes central not only in geometry, but in energy. The inner planets receive more sunlight and have higher surface temperatures, while the outer planets receive less and are colder. The distribution of sunlight is explained by the inverse square law, which means light spreads out as distance increases, so the same power is distributed over a larger area. This basic physical rule makes the solar system into a set of environments arranged by distance. Close to the Sun, rocks and metals are stable and can form solid worlds. Farther out, where sunlight is weaker and colder, conditions prevail. Lighter substances like water, ammonia, and methane can condense and remain as ice-shaping moons, and contributing to the composition of giant planets. In the outer planets, the worlds are not solid surfaces in the same sense. Jupiter and Saturn are gas giants with thick atmospheres and deep interiors where pressure and temperature rise with depth. Uranus and Neptune are often called ice giants because though they also have thick atmospheres, their interiors contain larger fractions of water, ammonia, and methane compounds under high pressure. These distinctions, while modern in their precise form, follow naturally from the solar system map, once temperature and material behavior are considered. The system is not a random collection. It is a gradient, a sequence set by distance from the Sun and by the conditions in the early protoplanetary disk, the rotating cloud of gas and dust from which the Sun and planets form. The protoplanetary disk model explains why planets orbit in roughly the same plane and in the same direction, and why there is a division between rocky inner planets and giant outer planets. The disk's angular momentum sets the overall alignment. Near the young Sun, heat prevents ices from condensing, so solid material is mostly rock and metal. Farther out, beyond a region often called the frost line, temperatures allow water and other volatiles to freeze and join the building blocks of planets, increasing the available solid mass and enabling the growth of large cores that can capture gas. This process layer, from environment to materials to formation, remains within the solar system, but it deepens the understanding of why the solar system is arranged as it is. It also frames the solar system as one example of a broader class of systems around stars, even before other systems are directly observed. Within this structured neighborhood, measurement continues to sharpen. The orbits of planets are not perfect circles. They are ellipses slightly stretched with the Sun at one focus. Their speeds vary faster when closer to the Sun and slower when farther into chord with conservation of angular momentum. These patterns are captured in laws of motion that can be tested against observation. Deviations from simple predictions, such as small changes in planetary positions over time, reveal gravitational interactions between planets. These interactions are not noise. They are part of the system's physics. They allow masses to be estimated because the way a planet perturbs another depends on its mass. Jupiter's influence on the motion of asteroids and comets, and on the other planets, becomes measurable. Saturn's influence follows. Over time, these calculations lead to increasingly accurate ephemerides, predictive tables of planetary positions, which in turn enable navigation and timing. The solar system becomes a clock-like structure whose predictability confirms the underlying physical model. Yet even as the solar system becomes more knowable, the sense of distance grows because each new improvement in measurement tends to increase, not shrink, the implied scale. The astronomical unit is large, and the outer planets are tens of astronomical units away. The boundary of the classical planets stretches out to Neptune at around 30 astronomical units. Beyond Neptune, smaller bodies populate belts and scattered regions. The Kuiper belt contains icy objects that orbit beyond Neptune, and farther still, a distant reservoir of comets is inferred, often called the Oort cloud. The Oort cloud is not directly imaged as a structure, but it is supported by the observed orbits of long-period comets. These comets arrive from all directions with very large, elongated orbits, suggesting a distant, roughly spherical distribution of icy bodies surrounding the solar system at tens of thousands of astronomical units or more. Even without a direct picture, the inference extends the solar system's reach far beyond the planets. The solar system is not just the region of the 8 major planets. It includes a vast outer population of small bodies, most of them dark and cold, moving slowly in the sun's weak grip. This is still within the sun's domain, still a local system, but its outer extent begins to approach the kind of distances where stellar space becomes relevant. Here, the earlier absence of stellar parallax returns as a boundary marker. If the Oort cloud reaches tens of thousands of astronomical units, then the nearest stars, still showing little or no shift with early instruments, must lie far beyond that. The solar system's outer envelope becomes a point of comparison. Even the largest plausible solar system distances remain tiny compared with the implied distances to stars. In this third section, the moment humanity realizes space may be too vast is not yet fully expressed as a number, but the conditions for that realization are created. A complete local map is built from the sun outward. Distances between planets are expressed in astronomical units, and the astronomical unit is expressed in kilometers. The solar system becomes a place with structure, temperature, gradients, and materials arranged by distance. Its outer boundaries expand to include belts and distant comet reservoirs. And as this local system becomes larger and more detailed, the star field remains unmoved by Earth's orbital baseline in early efforts. The contrast becomes sharper: a solar system that can be measured and a stellar realm that resists measurement. The outward journey in understanding has reached the edge of the sun's system. The next step inward toward the heart of the theme will be to take the same geometric discipline and apply it to the nearest stars, finally turning the absence of parallax into a detected signal and converting that tiny shift into distances that dwarf the solar system. For now, the solar system is fully entered and mapped as the immediate cosmic neighborhood, large in kilometers, yet still a single coherent system framed by a surrounding darkness whose scale is not yet pinned down but is already suggested to be far greater. The solar system's relative map becomes absolute when the astronomical unit is fixed with enough confidence that it can serve as a standard length, and this standard length changes how every other measurement is understood. The outer region here is not the farthest space, but the measurement framework itself, because the framework is what allows humanity to compare the solar system to anything beyond it. The astronomical unit begins as an idea, the average distance between Earth and the Sun, expressed in the same units as Earth's size. Over time, it becomes a number in kilometers. The path from idea to number passes through careful observation of rare alignments, steady accumulation of positional data, and the refinement of instruments and clocks. Once the astronomical unit is fixed, a second transformation follows. The solar system is no longer merely arranged in relative steps outward from the Sun. It becomes a calibrated space in which distances can be stated in the same units used for Earth. This calibration has a quiet but decisive effect on the sense of scale. A person can imagine Earth's circumference in kilometers and can relate it to travel on the surface. When the Earth-Sun distance is written in the same language, the gap becomes harder to integrate into ordinary intuition, yet it remains a concrete fact. From there, the distances to other planets, and then to the far outer reservoirs of comets, are no longer abstract ratios. They are enormous separations measured in familiar units that keep growing as the map extends outward. Within the solar system, the astronomical unit links to many kinds of observation. Planetary positions recorded over long periods can be fitted to gravitational models, and the best fit yields a scale consistent with the astronomical unit. The approach is iterative. A model predicts where a planet should appear in the sky on a given date and time. Observations test the prediction. Differences are measured in small angles, often arcseconds, even if that term is not used in the prose. The model is improved by adjusting parameters such as orbital elements and planetary masses. The astronomical unit is the bridge between the angular world of observations and the linear world of kilometers. As measurement improves, the astronomical unit's value becomes more stable and the uncertainty shrinks. In later eras, radar ranging provides a direct check. A radio pulse sent to Venus returns after a measurable delay. The delay is converted to distance using the speed of light, which is known from laboratory measurement. This gives a distance in kilometers between Earth and Venus at that moment. Coupled with orbital models, the astronomical unit is then determined with high precision. Even without emphasizing the modernity of radar, the important point is that the astronomical unit becomes anchored by multiple independent lines of measurement, making it trustworthy as a scale. With the scale trusted, the solar system becomes a place where linear speeds and travel times can be stated. Earth's orbital speed around the Sun is tens of kilometers per second. A spacecraft, when humanity later builds them, must reach similar speeds to move between planets. But in the present narrative, what matters is the conceptual consequence. The baseline created by Earth's orbit is enormous. Earth travels a full circle around the Sun each year. The diameter of that circle is 2 astronomical units, hundreds of millions of kilometers. This diameter becomes the measuring stick for the next outward leap because parallax measurements to stars depend on baseline. The outer region of the topic thus shifts from objects to geometry. Earth's orbit becomes the largest baseline humanity can use without leaving the solar system. It is an orbit traced by Earth itself, not by instruments moved across Earth's surface. To use this baseline, a star's position must be recorded with extraordinary precision over months, as Earth moves from one side of its orbit to the other. If the star is close enough, it will appear to shift against the background of more distant stars. The shift is tiny. It is smaller than the apparent width of any planet's disk. It is smaller than the blurring produced by the atmosphere for ground-based observation. Yet it exists, and when instruments become good enough, it is detected. The detection is not a new kind of physics. It is the same parallax principle used for the Moon scaled up with a much larger baseline and applied to much more distant targets. The first successful stellar parallax measurements reveal a simple, unsettling fact. Even the nearest stars have distances so great that the astronomical unit becomes inconvenient as a unit. The numbers would be too large for everyday use, so a new unit is introduced. The light year, the distance light travels in 1 year. Light's speed is finite and measurable, so light travel time can serve as a ruler. Another unit, the parsec, is based on parallax itself, defined so that a parallax angle of 1 second of arc corresponds to a distance of 1 parsec. But even without naming these units in detail at this moment, the conceptual shift is clear. The nearest star is not a few hundred astronomical units away. It is hundreds of thousands. When translated into kilometers, the distance becomes a number with many zeros far beyond solar system scales. This is one of the first places where the word vast becomes justified by measurement rather than impression. The astronomical unit, once itself an enormous step beyond Earth, shrinks into a small building block when used to express stellar distances. The solar system becomes a tiny neighborhood, and the space between stars becomes the new dominant feature. Yet Section 4 remains anchored in the astronomical unit and its role as a yardstick. It does not move fully into stellar space as a region yet. It stays at the boundary, showing how the yardstick is made reliable and how it points outward. The astronomical unit also supports another measurement idea, brightness, as a clue to distance. Once stars begin to have measured distances, their true luminosity can be inferred from their apparent brightness. A nearby star that appears modestly bright might be intrinsically similar to the Sun, while a star that appears equally bright but lies much farther away must be far more luminous. This relationship leads to the concept of standard candles objects, whose intrinsic brightness can be known, allowing distance to be estimated from how bright they appear. In the wider story, standard candles become crucial for mapping the galaxy and the universe. In this section, the astronomical unit is the first rung of a ladder. It fixes solar system distances, which allow stellar parallax distances, which allow calibration of brightness relationships. The entire enterprise depends on the yardstick being secure. If the astronomical unit is wrong, then everything above it is wrong. The effort to refine it is therefore foundational, and it is pursued with care. This yardstick also reshapes the understanding of the Sun. The Sun's diameter can be calculated from its angular size and its distance. With the astronomical unit known, the Sun's size becomes a number. Its energy output can be estimated from how much sunlight reaches Earth and how that energy spreads out in space. The Sun becomes not just a local light source, but a star with definable physical properties. When stars are later measured, comparisons become possible. A star's distance from parallax allows its luminosity to be determined, and then its size and temperature can be inferred if its spectrum is known. The astronomical unit thus quietly enables stellar astrophysics by making the Sun a calibrated reference and by allowing the first direct stellar distances. But the emotional core of the theme begins to take shape right here at the boundary. Humanity builds a ruler long enough to map the solar system, and then discovers that this ruler is still too short to make most stars show any shift. Even when the nearest stars finally yield a measurable parallax, the result places them at distances that make the solar system look compact. The solar system's outer regions, including distant comet reservoirs, remain deep within the Sun's gravitational reach, yet they are negligible compared with the gulf to the nearest star. The astronomical unit, the proud measure of planetary space, becomes a small step repeated hundreds of thousands of times. The realization is not sudden in tone, but it is decisive in implication. The universe of measured space expands outward by a jump, not a gradual stretch. The yardstick is secure, and the first star distances appear. With those two facts together, the boundary between solar system and stellar space becomes a boundary of scale. This is the moment when the question of vastness becomes grounded. It is no longer a poetic idea. It is a numerical comparison between the size of a known system and the empty distance to the next. The next outer region is the space between the Sun and the nearest stars, a region defined less by objects than by distance itself. With the astronomical unit secured as a reliable yardstick, and Earth's orbit recognized as a vast baseline, stellar parallax becomes the doorway to measured interstellar space. The method is a direct extension of earlier parallax work, but its demands are far stricter. The apparent shift of a nearby star over a year is extremely small, and it must be separated from other sources of apparent motion. Stars also have proper motion, a slow drift across the sky caused by their real motion through space relative to the Sun. Proper motion is not periodic. Parallax is periodic, repeating each year as Earth returns to the same points in its orbit. Precision observation must disentangle these components. The work requires stable instruments, careful calibration, and repeated measurements over long periods. When successful parallax measurements are obtained, the first distances to stars are not merely larger than solar system distances. They are so much larger that the solar system becomes a small point of reference. The nearest star system lies several light years away. A light year is the distance light travels in 1 year, and because light travels at a fixed speed, this unit ties distance to time directly. Even without relying on the unit itself, the translation to kilometers is staggering. The distance is many trillions of kilometers. This is not an estimate drawn from brightness or assumption. It is derived from geometry using Earth's orbit as a baseline. The result is the first measured statement that space between stars is mostly empty, and that the nearest star is not at the edge of the solar system, but far beyond it. The region between is not filled with planets or bright objects visible to the eye. It is dark, thin, and difficult to probe. Interstellar space is not a perfect vacuum, but it is close. It contains a very low density of gas, mostly hydrogen and helium, with trace heavier elements, and it contains dust grains made of silicates and carbon-rich material. The density is so low that the total mass in a vast volume can still be small. Yet this thin material matters because it affects starlight. Dust scatters and absorbs light, making distant stars appear dimmer and redder. This effect, called interstellar extinction and reddening, must be accounted for when using brightness to infer distance. In this section, the focus remains on the nearest stars, where parallax provides distance directly, and extinction is often modest. But the principle is introduced as part of what interstellar space is not emptiness alone, but a tenuous medium with measurable effects. Once the nearest stars are placed at measured distances, a second question emerges naturally within this region. What are these stars physically compared with the Sun? Parallax yields distance. Distance combined with observed brightness yields luminosity, the total light output. A nearby star that appears bright might still be less luminous than the Sun if it is very close, and a faint-looking star might be luminous but far away. When distance is known, apparent brightness stops being misleading. Many of the nearest stars are red dwarfs, smaller and cooler than the Sun, emitting less light. They are common in the galaxy, yet they are hard to see with the naked eye because they are faint. The brightest stars in the sky are often not the nearest. They are typically more luminous stars at greater distances. This mismatch between brightness and distance further deepens the sense of scale because it shows that the eye's map is not a distance map. The sky's familiar bright constellations are a mix of near and far. Parallax measurements begin to sort them, placing some stars relatively close and others far enough that their parallax is too small for early detection. The outcome is a layered star field, not a shell. The constellations remain as angular patterns, but their stars occupy different depths. Some are nearby within a few tens of light years. Others are hundreds of light years away or more. The patterns are projections, not structures. This is one of the most concrete ways vastness enters human understanding. A constellation that looks like a connected figure in the sky is not a connected object in space. Its stars are separated by great distances, and their apparent alignment is accidental from Earth's viewpoint. This is not a philosophical conclusion. It is a geometric fact confirmed by measured distances and proper motions. In this region, the idea of space as too vast becomes tied to travel and communication constraints. Even the nearest star is far enough that light itself takes years to cross the gap. A radio signal travels at the speed of light. If a signal is sent to a nearby star system, it would take years to arrive, and years for a reply to return, even if there were something there to respond. Physical travel is far more demanding. The fastest spacecraft humanity builds in its early spacefaring era reach speeds of tens of kilometers per second relative to the Sun. And even at such speeds, the journey to the nearest star would take many thousands of years. This is a simple division of distance by speed. It does not depend on advanced theory. It shows that interstellar distances are not merely large. They are large in a way that makes them effectively inaccessible with chemical rockets and current propulsion. This is a practical boundary that emerges directly from measured distances. The solar system can be explored over decades. Interstellar space cannot, at least not with the same methods. In the same region, another layer of understanding builds from the physics of stars. The Sun's energy is produced by nuclear fusion in its core, where hydrogen nuclei combine to form helium-releasing energy. This process requires high temperature and pressure found only deep inside the Sun. Other stars are powered by the same basic mechanism, though their internal conditions differ with mass. A star's mass largely determines its luminosity, temperature, and lifetime. Massive stars are brighter and hotter, but burn their fuel more quickly, living for shorter periods. Low-mass stars are dimmer and cooler, but can last far longer. This is relevant to the nearest stars because many are low-mass red dwarfs with long lifetimes, and they dominate the stellar population. The nearest star system includes such stars, and their faintness reinforces the lesson that the nearest is not always obvious. The galaxy around the Sun is filled with many faint stars unseen without telescopes. Once parallax opens the door to distance, the local stellar neighborhood becomes a three-dimensional map. Stars are placed in space around the Sun, and their motions are tracked. Proper motion combined with radial velocity measured by shifts in spectral lines yields full space velocities. The Sun itself is found to be moving through the local standard of rest, and nearby stars move relative to it in complex patterns. Some share similar motion, suggesting they formed from the same stellar nursery. Others pass through the region from different parts of the galaxy. The space between stars remains thin but not static. Gas clouds drift magnetic fields thread through the medium, and cosmic rays, high-energy particles, travel through it. These details are part of the local interstellar environment and influence the boundary of the solar system, shaping the heliosphere, the region dominated by the solar wind. The solar wind is a flow of charged particles from the Sun that expands outward until it meets interstellar material. At that boundary called the heliopause, the solar wind pressure balances the interstellar medium. This marks a physical edge of the Sun's influence in plasma terms, distinct from gravitational influence. The heliosphere is large compared with planetary orbits, yet it is still tiny compared with the distance to the nearest star. In this section, the local interstellar region becomes tangible through measurement and through physical description. The nearest stars are placed at distances that dwarf the solar system. The space between is recognized as an extremely thin medium that nonetheless leaves fingerprints on light and shapes the Sun's outer boundary. The constellations are revealed as projections of stars at different depths, separated by distances so great that the patterns have no physical unity. The practical meaning of vastness appears as travel time and signal delay, both tied to the finite speed of light. Humanity's ruler has reached beyond the solar system and touched the first stars. The result is a local map where the nearest neighbors are already far enough to make the region between them mostly empty. This is the step where vastness stops being an impression and becomes a measured fact expressed as years of light travel and as the near impossibility of crossing the gap with familiar speeds. Once the nearest stars are placed at measured distances, the outer region shifts from geometry alone to the combination of geometry and a universal physical limit, the finite speed of light. Light does not arrive instantly. It travels at a fixed speed in vacuum, and that speed ties distance to time in a direct way. In earlier regions, time is used to mark cycles in the sky and to record planetary periods. Here, time becomes a distance tool. A light year is defined as the distance light travels in 1 year, and this definition is not symbolic. It is practical. When a star is 4 light years away, the light reaching Earth today left that star 4 years earlier. The star is not seen as it is in the present moment, but as it was in the recent past. This is the first step in a progression that will later extend to millions and billions of years when observing galaxies. In the local region, the time delay is small enough to be grasped, yet large enough to make the limit clear. Communication and observation are constrained by light travel time, and no signal can outrun it. This is not a matter of engineering difficulty. It is a property of nature as understood by modern physics and confirmed by experiment. The speed of light becomes part of the structure of space, setting a horizon of cause and effect. Within the nearby stellar neighborhood, light travel time immediately affects how distance is measured beyond parallax. Parallax remains the gold standard for nearby stars, but it becomes hard for more distant stars because the parallax angle shrinks with distance. To reach farther, astronomy uses other methods that depend on light and on the properties of objects that emit it. These methods form a distance ladder, a sequence where one method calibrates the next. The ladder begins with the astronomical unit and stellar parallax, which provide absolute distances to nearby stars. Once those distances are known, the intrinsic brightness of certain kinds of stars can be determined. If a class of objects has a reliable relationship between an observable property and its true luminosity, then its distance can be inferred from how bright it appears. This is where light becomes a ruler. The relationship must be anchored by nearby examples whose distances are known from parallax. In the realm just beyond the nearest stars, one of the most important classes is Cepheid variable stars. A Cepheid varies in brightness with a regular period. The period is linked to the star's intrinsic luminosity. By measuring the period of a Cepheid and using the calibrated relationship, the star's true luminosity is estimated. Comparing true luminosity to observed brightness yields distance. This technique extends the distance scale far beyond parallax. It is still grounded in measurement, but it requires careful correction for dust and for the properties of the star's environment, because interstellar extinction can dim light and mimic greater distance. The use of Cepheids shows how the finite speed of light is both a limit and an opportunity. Light carries information across space, but it also arrives with delay. The longer the distance, the older the information. The night sky becomes a collection of times as well as places. Even within the Milky Way, some objects are seen as they were thousands of years ago. The region begins to gain depth in time. Alongside variable stars, another way light becomes a ruler is through spectroscopy, the analysis of light split into its component wavelengths. A star's spectrum reveals its surface temperature composition and motion along the line of sight. Motion is measured by Doppler shift, a change in wavelength caused by the star moving toward or away from Earth. In the local region, Doppler shifts allow measurement of radial velocities. Combined with proper motions and distances, they yield three-dimensional velocities. This turns the local stellar neighborhood into a dynamic system. Stars are not fixed markers. They move through the galaxy. Their motion changes the sky slowly over time. Constellations will not keep their shapes over tens of thousands of years. This is another way vastness becomes concrete. The sky's apparent stability is only a short-term effect of human lifetimes. On longer timescales, the patterns dissolve. Yet within the calm pace of the narrative, this is not treated as drama. It is treated as a measured consequence of stars moving at tens of kilometers per second over interstellar distances. Even small angles on the sky correspond to enormous linear distances when stars are far away. The speed of light also clarifies the nature of stellar energy and the information carried by starlight. Light from a star encodes what is happening at the star's surface, and in some cases, what happens in its interior, through oscillations and spectral changes. It also encodes the intervening medium. Dust leaves a fingerprint by preferentially dimming shorter wavelengths, causing reddening. Gas clouds produce absorption lines at specific wavelengths. Magnetic fields influence polarization. Thus, interstellar space, though thin, becomes detectable through the way it modifies light. The local interstellar medium can be mapped by observing how starlight changes with direction. Regions with more dust show greater extinction. Regions with certain gas compositions show specific absorption features. This mapping remains within the outer region of nearby space, but it shows that emptiness has structure. The vast distances are not filled with dense matter, yet they are not featureless. They contain diffuse clouds, cavities, and boundaries shaped by past supernova explosions and stellar winds. In the local neighborhood, one such feature is the local bubble, a region around the Sun, with relatively low-density hot gas thought to be produced by past supernova in the broader region. The exact history and details remain an area of active research, but the existence of low-density cavities and warmer regions in the interstellar medium is supported by observations across multiple wavelengths, including X-rays and ultraviolet absorption studies. The narrative states what is known: the Sun lies in a structured interstellar environment. It avoids unwarranted certainty about the precise sequence of supernova events. The finite speed of light also sets the pace at which the solar system's own probes can report back. When spacecraft travel to the outer solar system, the radio signals they send take hours to reach Earth, not years, because the distances are in light hours. This contrast is instructive. Within the solar system, even at Neptune, light travel time is hours. To the nearest star, it is years. This difference is not a matter of small versus large. It is a change in category. A system where communication delays are measured in minutes or hours behaves differently from one where delays are measured in years. Planning control and even the idea of interaction changes. This brings the notion of too vast into a practical domain again, but now framed by light. The speed of light makes the universe observable in principle across enormous distances because light can travel for billions of years and still arrive. At the same time, it limits real-time connection and makes the far universe unavoidably a view of the past. In this sixth section, the focus stays near enough that the delays are years to thousands of years. Not yet the deep cosmic past, but the principle is fully established. Light is the messenger and the measuring tape. Time becomes distance. The local stellar neighborhood becomes a set of positions and velocities derived from light and geometry. Distance ladders begin to form extending reach beyond direct parallax. Interstellar space becomes a medium whose properties are read from the changes it imposes on starlight. The calm, neutral conclusion of this region is that once the speed of light is taken seriously as a fixed limit, the scale of space becomes inseparable from the scale of time. The nearer stars are not just far away. They are far away in a way that rewrites what it means to see and to measure. The next outward step will take this light-based ruler and apply it to the structure of the Milky Way itself, where dust star counts and calibrated distances reveal a vast system of stars within which the Sun is only one member. With distance and light joined into a practical measuring system, the outer region now becomes the Milky Way as an extended physical system, rather than a bright band across the sky. The Milky Way begins as a naked-eye phenomenon, a pale, uneven glow stretching across the night, brighter in some places and dimmer in others, crossed by darker patches. For a long time, it can be taken as a cloud-like feature on the celestial sphere. The change comes when telescopes resolve the glow into countless faint stars. The band is not a continuous luminous substance. It is the combined light of vast numbers of stars, too faint to be seen individually without magnification. This resolution is the first step toward understanding the Milky Way as a stellar system with depth and structure. Yet even with telescopes, the Milky Way's shape is not immediately clear because the observer is embedded within it. Looking along the plane of the galaxy, the line of sight passes through dense star fields and through interstellar dust that blocks and reddens light. Looking away from the plane, the sky appears thinner with fewer stars. This contrast hints at a flattened structure like a disk, but mapping it requires distances, and distances require reliable methods beyond the nearest neighborhood. This is where the distance ladder and the behavior of light become essential. To map the Milky Way, astronomers use standard candles and other distance indicators to place objects in three-dimensional space. Cepheid variable stars are among the most important tools because their period luminosity relationship allows their distances to be estimated at scales beyond parallax. When Cepheids are found in star clusters, their distances help calibrate the cluster distances and support a broader framework for stellar populations. Another key tool is the study of star clusters themselves. Open clusters tend to lie in the disk and contain younger stars. Globular clusters are older, dense collections of stars that orbit the galaxy in a more extended halo. Their distribution becomes particularly informative. By measuring distances to many globular clusters, a pattern emerges. They are not centered on the Sun. They are concentrated toward a region of the sky in the direction of the constellation Sagittarius. This suggests that the center of the Milky Way lies in that direction far away, and that the Sun is located at a substantial distance from the center. This conclusion does not require seeing the center directly in visible light. Interstellar dust blocks the view. Instead, it comes from mapping the positions of clusters and the overall symmetry of their distribution. As these measurements accumulate, the Milky Way stops being a local glow and becomes a large system with a central region and a periphery. The scale is vast compared with the solar system, and even compared with the local interstellar neighborhood. Distances across the galaxy are measured in thousands and tens of thousands of light years. The Sun's distance from the galactic center is measured in tens of thousands of light years. This is the point where the term vast becomes unavoidable in a measured sense. The gap to the nearest star is a few light years. The span of the Milky Way is tens of thousands across. Even at the speed of light, crossing the galaxy would take tens of thousands of years. At the speed of spacecraft, it would take far longer. The galaxy becomes a structure too large to be navigated in any practical way by material travel with familiar propulsion and it is large enough that its internal processes unfold on timescales beyond human history. Yet it is not undefined. It has components and patterns that can be described. The Milky Way has a disk where most of the stars and gas lie, including spiral arms regions of higher density, where star formation is active. It has a central bulge, a thicker, denser region of stars near the center. It has a halo, a roughly spherical distribution of older stars and globular clusters, and a surrounding dark matter halo inferred from the motions of stars and gas. Dark matter is not observed directly through light, but its presence is inferred because the visible mass of the galaxy cannot account for the observed rotation speeds at large radii. Stars and gas in the outer galaxy orbit faster than would be expected if only the visible matter were present. This inference is supported by multiple lines of evidence across astrophysics. In this section, the narrative treats dark matter cautiously. It is a well-supported inference from gravitational effects, but its particle nature remains unknown. The Milky Way's shape is not perfectly known from within, but multiple observations converge. Radio astronomy becomes crucial because radio waves can pass through dust that blocks visible light. The galaxy contains neutral hydrogen gas that emits radiation at a wavelength of 21 centimeters. Mapping this emission across the sky reveals the distribution of hydrogen in the disk and helps trace spiral structure. By measuring Doppler shifts of the hydrogen line, astronomers can infer the motion of gas and construct a rotation curve for the galaxy. This is a step in the outer to inner path from visible appearance to internal dynamics. The Milky Way becomes a rotating disk with material orbiting the center. The rotation is not rigid. Inner regions orbit faster than outer regions, and the pattern reveals the distribution of mass. In the central region, radio and infrared observations penetrate dust and reveal dense star fields and complex gas dynamics. There is strong evidence for a supermassive black hole at the center, inferred from the orbits of stars around an unseen mass concentrated in a small volume. These measurements show that stars near the center move at very high speeds on tight orbits, requiring a central mass of millions of solar masses. The black hole itself is not directly visible, but its gravitational influence is measured. This adds another layer to the galaxy's inner structure, but in this section, the focus remains on the overall mapping. The Milky Way is a vast system with a center, and the Sun is not at that center. Dust complicates the map, but dust is also part of the galaxy's material reality. Dark lanes in the Milky Way band are regions where dust clouds block starlight. These clouds are also the raw material for new stars. In dense regions of gas and dust, gravity can cause collapse, forming protostars surrounded by disks. Over time, nuclear fusion ignites and new stars shine. Star formation is therefore tied to the galaxy's structure. Spiral arms are not solid structures, but regions where density waves compress gas, triggering star formation. The youngest, brightest stars and the glowing gas of emission nebulae outline these arms. Older stars drift away over time. This gives the Milky Way a layered appearance depending on what kind of light is observed. Visible light highlights young stars and dust-obscured regions. Infrared light penetrates dust and reveals cooler stars. Radio maps gas. X-rays reveal high-energy sources like supernova remnants and accreting compact objects. Each wavelength adds a different layer to the same system. The Milky Way's vastness is thus not only in its size, but in the complexity that emerges when different forms of light are used. In this seventh section, the band in the sky becomes a disk of stars and gas extending tens of thousands of light years with spiral structure, a central bulge, and a halo. The sun's position becomes a point in that disk not privileged. The map is built through standard candles, cluster distributions, and radio observations that see through dust. The concept of vastness shifts again. It is no longer only the emptiness between stars. It is also the sheer number of stars and the scale of a system that contains them. The Milky Way is large enough that the nearest star is only a local neighbor within a much larger city of stars, and the Sun's planetary system is a small detail within one spiral arm region. The next step inward will be to place the Sun precisely within this structure, to quantify its offset from the center, and to show how that relocation changes the sense of where humanity is when it looks outward. Once the Milky Way is understood as a vast rotating disk with a central region, the outer region shifts to the Sun's true location within that system, and to the measured consequences of not being at the center. The earlier sky-based intuition places Earth and then the Sun in a privileged position, because the sky appears to rotate around the observer and the Sun appears to govern the day. Even after the solar system becomes sun-centered, the Sun can still seem like the natural center of the wider cosmos by habit. The Milky Way map breaks that habit through measurement. The distribution of globular clusters points to a galactic center far from the Sun. The concentration of star fields and gas toward the direction of Sagittarius supports that location. Radio and infrared observations reveal a dense, dynamic central region that is heavily obscured in visible light. The Sun is measured to be far out in the disk, at a distance of tens of thousands of light years from the center. This distance is not a guess. It comes from multiple methods that converge. Standard candles such as Cepheids and other variable stars provide distances to regions in the disk. The geometry and distribution of clusters provide a center direction and center distance. The motions of gas traced by radio emission, interpreted with a rotation model, give a consistent picture of a rotating disk with the Sun at a particular orbital radius. In this region, the narrative remains calm and procedural. The Sun is placed by measurement, and the implications are treated as practical consequences rather than as meaning. One immediate consequence is perspective. From the Sun's location in the disk, the Milky Way band appears brighter in some directions and dimmer in others, because the line of sight through the disk varies. Looking toward the galactic center, the line of sight passes through more stars and more dust, producing a brighter but more obscured band. Looking away from the center toward the outer disk, the line of sight encounters fewer stars before leaving the disk, producing a dimmer band. This explains the uneven brightness of the Milky Way as seen from Earth. It also explains why early maps of the galaxy can be misleading if dust is not properly accounted for. Dust blocks visible light more strongly in the plane, so distant regions can be hidden. This can make the galaxy appear smaller or differently shaped if measurements rely only on visible star counts. The correction comes by using infrared and radio wavelengths that penetrate dust and by using distance indicators that can be corrected for extinction. Another consequence is dynamical. The Sun is not stationary within the galaxy. It orbits the galactic center, taking hundreds of millions of years to complete one circuit. The orbital speed is on the order of a few hundred kilometers per second. This can be inferred from the rotation curve and from the Sun's motion relative to nearby stars and gas. Over the Sun's lifetime, it has completed many orbits. This means the solar system's position within the Milky Way changes with time passing through regions of different stellar density. The spiral arms themselves are not rigid structures, so the Sun may drift relative to them. The local interstellar environment can change as the solar system moves through different gas clouds. In the present narrative, these changes are stated as possibilities grounded in the measured motion and structure without speculative detail about specific past crossings. The important point is that the Sun's location is one point on a move-in orbit within a vast disk, and that the galaxy's scale makes such motion relevant over geological time. A third consequence concerns the interpretations of stellar populations. Different regions of the galaxy have different kinds of stars. The disk contains many young stars and active star-forming regions, especially along spiral arms. The bulge contains older stars on more random orbits. The halo contains very old stars and globular clusters. By placing the Sun in the disk, it becomes clear that the stars in the night sky visible to the naked eye are a biased sample dominated by relatively nearby and relatively luminous stars in the disk. The faint red dwarfs, though numerous, are mostly invisible without telescopes. The halo stars, though old, are sparse. The bulge is heavily obscured by dust in visible light. This explains why the night sky does not reveal the galaxy's true mass distribution. It also explains why the Milky Way's overall structure must be inferred from targeted surveys rather than simple inspection. The relocation of the Sun away from the center also influences how distances within the galaxy are measured. When mapping spiral arms, astronomers must account for the fact that they are viewing from an off-center position inside the disk. Spiral patterns that are simple to see from outside are difficult to reconstruct from within because of overlapping lines of sight and dust obscuration. Radio maps of hydrogen and molecules help by tracing gas throughout the disk, and distances can be estimated using Doppler shifts and a rotation model. However, this method has limitations. It depends on the assumed rotation curve and can produce distance ambiguities in certain directions, especially inside the Sun's orbit, where the same radial velocity can correspond to two different distances along the same line of sight. These uncertainties are resolved by combining methods parallax to star-forming regions measured with very long baseline interferometry in radio wavelengths, distances to masers, and the use of standard candles in infrared. As data improve, the map of the Milky Way's spiral arms becomes more detailed, revealing that the galaxy has multiple arms and spurs, and that the Sun lies in a smaller feature often called the local arm or Orion spur between larger spiral arms. The naming is less important than the placement. The solar system is not in the densest star-forming region, and not near the center, but in a relatively moderate part of the disk. The galaxy's center itself becomes a defined place with measured properties. In the central region, the orbits of stars around an unseen compact mass indicate a supermassive black hole. The mass is measured to be millions of times that of the Sun. The existence of this central mass is supported by precise tracking of stellar motions over years and decades, showing Keplerian orbits around a common focus. The black hole's presence is part of the inner structure, but its significance here is that it provides a central anchor for the galaxy's gravitational field and helps define what is meant by the center. The Sun's orbit is around this center. The galaxy's rotation and the distribution of mass are organized around it. The Sun's offset is therefore not merely a statement of position. It is part of a dynamical system. With the Sun placed, the scale of the Milky Way becomes more graspable in comparative terms. The distance from the Sun to the galactic center is tens of thousands of light-years. The thickness of the disk is much smaller than its diameter, indicating a flattened structure. The halo extends much farther, containing globular clusters at large distances. The total number of stars in the Milky Way is enormous, on the order of hundreds of billions, though exact estimates vary and depend on assumptions about stellar populations and faint stars. In this section, such numbers are treated cautiously, emphasizing that the galaxy contains a vast population and that the estimate is constrained by surveys and models with uncertainty at the margins. The overall picture is still firm. The Milky Way is a massive galaxy, and the Sun is one star within its disk. The theme of vastness deepens because the observer's place is no longer central and because the scale of the system is now anchored by a center far away. When humanity realizes the Sun is not at the center of the galaxy, the sky becomes less like a surrounding shell and more like a view from within a large, structured environment. The Milky Way band is understood as looking along the disk, and its brightness variations reflect the Sun's offset location. The stars are understood as members of a rotating system whose scale makes individual lifetimes small in comparison to galactic dynamics. This relocation sets up the next outward leap. If the Milky Way is one galaxy with a center far away, the question becomes whether the faint nebulae seen in telescopes are part of this same system or separate systems at distances far beyond the Milky Way's size. The methods that placed the Sun will now be turned outward again, using light-based distance indicators to cross the boundary from the Milky Way to other galaxies. The outer region now lies beyond the Milky Way's borders at the boundary where faint smudges in telescopes are tested to determine whether they belong to the same galactic system or represent separate star systems at far greater distances. Before this boundary is crossed, the Milky Way can be treated as the primary container of stars. The sky holds clusters nebulae and the hazy band of the galaxy itself, and many faint patches of light appear as unresolved clouds. Some of these patches are clearly local. Gas clouds glow where nearby stars energize them, and dark clouds block starlight in visible wavelengths. Star clusters resolve into individual stars with sufficient magnification. Yet a class of objects persists as stubbornly unresolved or only partly resolved, showing spiral structure in some cases when observed carefully. These are often called spiral nebulae in early accounts because their nature is uncertain. The key question is distance. If these objects lie within the Milky Way, they are comparatively nearby and modest in size. If they lie far outside, they must be enormous collections of stars comparable to the Milky Way itself. The only way to decide is through measurement, and measurement depends on the same distance ladder built from the astronomical unit parallax and calibrated standard candles. The decisive step comes when variable stars are identified within these spiral objects. Cepheid variables are particularly useful because their periods can be measured from repeated observations, and their intrinsic luminosities can be inferred from the period-luminosity relationship calibrated using closer Cepheids, whose distances are known. The method is straightforward in logic and careful in practice. An observer records the brightness of a candidate Cepheid over time, establishing its period. The period then indicates how luminous the star truly is. Comparing that true luminosity with the observed brightness yields distance once corrections are made for extinction by dust and for the observational limits of the instruments. When Cepheids are measured in nearby spiral objects, the distances that result are far larger than the size of the Milky Way. The objects cannot be small clouds within the galaxy. They must be separate galaxies, each containing vast numbers of stars. This is the moment when the scale of the universe expands again, by a large jump, not by gradual extension. The Milky Way ceases to be the whole. It becomes one galaxy among many. The sky is no longer a view across a single disk from within. It becomes a view outward into a much larger population of star systems separated by intergalactic space. The nature of these external galaxies becomes clearer as observations improve. Some show spiral arms and central bulges, suggesting rotating disks with star formation patterns like those inferred for the Milky Way. Others appear as smooth, featureless ellipses dominated by older stars and lacking obvious spiral structure. Some are irregular, disturbed, or interacting. The classification is not merely a matter of appearance. It reflects differences in stellar populations, gas content, and dynamical history. In this region, the main point is that each galaxy is a system on the scale of the Milky Way, and the distances between them are far larger than the distances between stars within a galaxy. Intergalactic space is even thinner than interstellar space with lower densities of gas, though it is not perfectly empty, and it contains diffuse plasma and traces of heavier elements. The main feature of the region is separation. The nearest large external galaxies are hundreds of thousands to millions of light-years away. These distances are so large that even light takes long times to cross them, and any physical travel at familiar speeds becomes entirely impractical. The earlier contrast between solar system distances and star distances repeats at a new level. A light-year once expresses the gulf to the nearest stars. Now millions of light-years express the gulf between galaxies. The sense that space is too vast begins to take a firm shape here, because the ladder of measurement has crossed from local to extragalactic and has not found a boundary. Instead, it reveals more structure at larger scales. The evidence does not rely only on Cepheids, though Cepheids provide a clean and historically important rung. Other distance indicators support the same conclusion. The brightest stars in a galaxy have a limit to their luminosity, and the brightness distribution of certain stellar populations can be compared across systems. In later developments, specific transient events such as Type 1, a supernovae, serve as standardizable candles because they reach similar peak luminosities under known conditions, allowing distances to be measured across very large scales. But within the present region, the essential mechanism is the calibration of light-based measurements against local geometric measurements. A ladder is only as trustworthy as its lower rungs, and the astronomical unit and stellar parallax remain at the base. The careful chain from Earth's orbit to nearby stars to variable stars and then to external galaxies makes the conclusion robust. Once external galaxies are established as real systems at enormous distances, the Milky Way is reframed. Its size can be compared to the sizes of other galaxies. Its stellar content becomes one example among many. Its spiral structure can be inferred by analogy and by internal mapping, while other galaxies provide direct external views of similar structures. This comparison supports a more accurate understanding of the Milky Way's own form, because looking at other spirals shows what a disk galaxy can look like from the outside, including how spiral arms wrap, how bars can exist across central regions, and how dust lanes trace dense gas. It also highlights that galaxies evolve. Interactions and mergers can distort shapes, trigger star formation, and rearrange stellar orbits. In the outer region of extragalactic space, galaxies are not isolated points. They can be part of groups and clusters bound by gravity. The Milky Way itself belongs to a small group with its nearest large neighbors, and larger clusters exist at greater distances containing hundreds to thousands of galaxies. The existence of clusters adds another layer to the scale. If a single galaxy is tens of thousands of light-years across a cluster, spans millions of light-years. Yet even clusters are not evenly distributed. Galaxies tend to gather in filaments and walls with large voids between. This broader structure will be addressed later, but in this section, the first step is the recognition that galaxies exist beyond the Milky Way, and that the universe contains many of them. The observational sky changes accordingly. Many of the faint smudges seen in telescopes are not clouds within the Milky Way, but distant galaxies, each with its own stars, dust, and gas. The night sky is therefore a layered view across vast depths. Nearby stars are foreground. The Milky Way's own star fields and dust are midground. External galaxies are background at enormous distances. The light from these galaxies reaches Earth after long travel times. A galaxy seen 2 million light-years away is seen as it was 2 million years ago. This is still modest compared with the deep cosmic look-back time that will come with more distant galaxies, but it establishes the principle in an extragalactic context. Observation becomes history by necessity, because of the finite speed of light. Another consequence is a change in how humanity interprets the scale of the visible universe. The Milky Way's diameter, large as it is now only 1 unit. The distances to other galaxies are measured in multiples of that diameter many times over. Intergalactic space becomes the dominant volume. If stars are separated by light-years, galaxies are separated by hundreds of thousands to millions of light-years. The ratio is so large that the density of luminous matter in the universe appears low when averaged over large volumes. Most of space is not filled with stars or planets, but with darkness and thin gas. The meaningful structures are concentrated islands of matter bound by gravity. The recognition of external galaxies thus intensifies the earlier understanding of emptiness, not as an absence of interest, but as a measured feature. It also sets the stage for a new kind of measurement, based on the behavior of light over large distances. As distances extend, the spectra of galaxies show systematic shifts in their wavelengths. These shifts, called redshifts, can be interpreted as evidence of motion away from the observer and at very large scales as a sign of cosmic expansion. That step belongs to the next region. For now, Section 9 remains with the boundary crossed itself. The spiral nebulae are not clouds in the Milky Way. They are galaxies. The ladder of distance reaches outward, and instead of finding an edge, it finds a new population of systems, each immense, separated by distances that make earlier scales seem small. The measured conclusion is quiet and stark. The universe is not a single galaxy with a few nearby objects. It is a vast field of galaxies, and the Milky Way is one among them. With external galaxies established as separate systems at immense distances, the outer region shifts to the large-scale behavior of space itself inferred from the light that arrives from those galaxies. The key observation is spectral shift. When light from a galaxy is spread into a spectrum, recognizable lines appear produced by atoms and molecules absorbing or emitting light at specific wavelengths. In a laboratory on Earth, these lines have known wavelengths. In many galaxies, the same pattern of lines appears, but shifted toward longer wavelengths. This shift is called redshift. It can be measured precisely by comparing the observed wavelengths with the known rest wavelengths. In a simple interpretation, a redshift indicates that the source is moving away along the line of sight, because motion away stretches the light's wavelength through the Doppler effect. For nearby galaxies with relatively small redshifts, this interpretation works well as a description of recessional motion. The crucial next step is to connect redshift to distance, and that requires distances measured independently of redshift, so that the relationship can be tested rather than assumed. The distance ladder provides those independent distances. Cepheid variables in nearby galaxies give distances to those galaxies. Other methods extend the ladder, the brightness of the tip of the red giant branch in old stellar populations, certain properties of galaxies that correlate with luminosity, and later the use of Type 1a supernovae as standardizable candles. In the early establishment of expansion, the essential point is that for a set of galaxies whose distances are determined by these non-redshift methods, the measured redshifts tend to increase with distance. The farther the galaxy, the larger the redshift. When plotted as recessional velocity versus distance, the relationship is approximately linear over a range of distances where the data are available. This relationship becomes known as the Hubble law, and the constant of proportionality becomes the Hubble constant. The law does not state that every galaxy moves through space away from a central point. Instead, the simplest modern interpretation is that space itself is expanding so that the distance between gravitationally unbound galaxies grows over time. In this picture, galaxies are largely carried along with the expanding fabric of space on large scales, while remaining bound within local systems, such as galaxies, galaxy groups, and clusters. The expansion is not a force that tears apart bound systems at ordinary scales. It is a large-scale behavior that becomes apparent when comparing galaxies separated by millions and billions of light-years. The evidence for expansion is therefore built from a combination of precise spectral measurement and independent distance estimation. The redshift distance relation is not derived from a single observation, but from repeated measurements across many objects, and its reliability grows as methods improve and samples expand. In this region, it is important to treat the interpretation with care. Redshift can have contributions beyond the simplest recessional motion. Galaxies also have peculiar velocities, additional motions, due to local gravitational interactions. A galaxy within a cluster can move toward or away from the cluster center, while the cluster as a whole participates in cosmic expansion. These peculiar velocities can blur the redshift distance relationship at small distances, where local motions can be comparable to the recessional speed implied by expansion. As distances increase, the expansion-related component grows and dominates over typical peculiar motions, making the overall trend clearer. Another source of complexity is measurement uncertainty in distances. The distance ladder relies on calibrations, and each rung introduces potential systematic errors. Cepheid-based distances depend on understanding Cepheid populations, metallicity effects, and extinction by dust. Supernova-based distances depend on standardization techniques and corrections for dust and host galaxy properties. Despite these challenges, the overall conclusion of expansion is supported by multiple independent distance indicators and by consistent results across different methods. In modern cosmology, expansion is also supported by additional evidence, including the cosmic microwave background and the large-scale distribution of galaxies. But within the present region, the focus remains on the observational relationship between redshift and distance, established from galaxy spectra and distance ladder measurements. Once expansion is accepted, the scale of the universe changes again in a measured way. If redshift increases with distance, then the far universe is not only far in space, but also far in time. Because light takes time to travel, distant galaxies are seen as they were long ago. Expansion adds another layer. The light has its wavelength stretched during its journey, and the rate of stretching is connected to the history of expansion. The universe becomes describable with a timeline that is read from light. A galaxy with a larger redshift is not merely farther away. It is seen at an earlier stage in cosmic history, and its light has traveled for a larger fraction of the universe's age. This introduces the idea of look-back time as a central concept. Look-back time is not a separate measurement from distance. It is the time light has spent traveling from source to observer. For nearby galaxies, look-back times are small compared with human history, but for distant galaxies they become millions and then billions of years. In this section, the narrative stays with the first step of that progression, where expansion is inferred, and the idea of time depth becomes necessary. The practical meaning of expansion also connects back to the theme of vastness. Before expansion is known, the universe can be imagined as large but static, potentially infinite, or potentially bounded without a clear way to connect its scale to a history. With expansion, a measurable rate appears. The Hubble constant expresses how fast the universe expands per unit distance at the present epoch, though its value is measured with uncertainty and has been refined over decades. The reciprocal of this constant gives a timescale which provides an approximate age scale for the expansion, though the true age depends on the detailed expansion history and the contents of the universe, including matter radiation and dark energy. The important point is that expansion connects distance to a time framework, making the universe not only large, but dynamically evolving. This is where humanity's sense of vastness can shift from a spatial problem to a combined space-time problem. The universe is too vast to traverse, and it is also too vast in time to be observed in a single state. Because looking farther automatically means looking earlier. The observational universe becomes a layered archive. The same light-based methods that made the Milky Way a system and external galaxies real now show that the space between galaxies is not static. It is changing in a systematic way that can be measured. Within this region, it is also necessary to state what remains uncertain without speculation. The precise value of the Hubble constant has long been an area of active research with different measurement approaches, sometimes yielding values that are in tension. One approach uses the distance ladder, combining Cepheids and Type I, a supernovae, to infer the expansion rate in the nearby universe. Another approach infers the expansion rate from observations of the early universe, particularly the cosmic microwave background within a cosmological model, then extrapolates to the present. If these approaches disagree beyond expected uncertainties, it could indicate unrecognized systematic errors, or it could indicate that the simple model needs refinement. The present consensus is that expansion is real and well established, while the exact rate and the reconciliation of different measurements are subjects of ongoing work. This statement stays within what is known multiple lines of evidence support expansion, and precision cosmology continues to refine parameters and resolve tensions. The broad picture remains stable. Galaxies on large scales show redshifts that increase with distance. The universe expands. This expansion implies that at sufficiently large distances, recession speeds can be very large, and in the framework of expanding space, recession can exceed the speed of light without violating the rule that no object locally travels through space faster than light. This distinction is subtle and belongs to the structure of general relativity, where expansion is a property of space-time geometry rather than a conventional velocity through space. The consequence for observation is clear. There is an observable limit set by the finite age of the universe, and the speed of light and expansion shapes what can be seen from the present. That limit is not reached in this section, but it becomes the next outward boundary to describe. For now, Section 10 remains with the moment of expansion becoming an observational conclusion. Spectra show redshift. Distances measured independently show a trend. The trend implies large-scale expansion. The universe is not merely vast as a static arena. It is vast and changing, and its size and history are connected through light. The measured realization is that as distances extend beyond the Milky Way to the realm of galaxies, the dominant feature is not only the separation between islands of stars, but the systematic stretching of space between them. This is the point where the scale of space becomes inseparable from the idea of a cosmic history, and where the vastness is expressed not only by the number of kilometers and light-years, but by the fact that looking outward is also looking back. With expansion established as a measurable property of the universe, the outer region now becomes the limit of what can be observed at all, a limit set by the finite speed of light, the finite age of the universe, and the way expansion changes distances over time. This limit is often described in terms of a horizon. A horizon in this context is not a physical wall. It is a boundary in space-time that separates events whose light can reach an observer from events whose light cannot give in the universe's history. The most immediate concept is the observable universe, the region from which light has had time to reach Earth since the beginning of cosmic expansion. Because the universe has a finite age, light from regions beyond a certain distance has not yet arrived. Even if those regions exist, they remain unobservable in principle at the present time. The boundary of the observable universe is therefore a boundary of information, not a boundary of matter. The observable radius is not simply the age of the universe multiplied by the speed of light, because expansion means that the space through which light travels can stretch while the light is in transit. As a result, the present-day distance to the farthest observable sources can be much larger than the light travel distance would suggest in a static universe. This is a subtle but essential feature. Light emitted long ago from a distant region can travel toward the observer while the intervening space expands. By the time the light arrives, the source region may be much farther away than it was when the light was emitted. The observable universe is thus defined by what can be seen, but the distances involved depend on the expansion history. This region is where human intuition based on static space fails most strongly. The measured conclusion is that there are distances that can be defined in different ways. Light travel time, comoving distance, proper distance at the present epoch, and look-back time. Each is meaningful in a different context. Look-back time tells how long the light has been traveling. Proper distance tells how far away the source is now at the time of observation in a chosen cosmological model. Comoving distance factors out expansion to track positions in the expanding coordinate grid. These concepts are technical, but they can be stated plainly once distance in an expanding universe depends on how the expansion is accounted for, and different definitions answer different questions. The key for the narrative is that the observable universe has a finite boundary, and the boundary is shaped by expansion. A second horizon concept is the particle horizon, the maximum distance from which particles or light could have traveled to the observer since the beginning. This is closely related to the observable universe. Another is the event horizon, the boundary beyond which events that occur now will never be able to influence the observer in the future, because expansion will carry those regions away too fast. The existence and size of an event horizon depend on the universe's long-term expansion behavior, particularly whether expansion accelerates. Modern observations indicate that the universe's expansion is accelerating at the present epoch, attributed to a component called dark energy. Dark energy is not observed directly, but inferred from the way expansion changes over time, most notably from observations of distant Type 1, a supernova, along with other cosmological data sets. The acceleration implies that there are regions whose light emitted now will never reach us in the far future. This adds another layer of limit. Not only is there a finite observable region at present, but the set of regions that can ever be observed may be finite as well. This is stated as an inference within the standard cosmological model, while noting that the physical nature of dark energy remains unknown. The point is not to dwell on the mechanism, but to describe the observational consequence. Expansion can create horizons that restrict what can be connected by light signals over cosmic times. In the context of vastness, this is a profound change. Earlier vastness is a matter of large numbers and long travel times. Here, vastness includes fundamental inaccessibility. Some regions are not merely far, they are beyond contact. Even light cannot bridge the gap within the universe's lifetime or within its future evolution as currently understood. This is a measured statement based on cosmological parameters, not a metaphor. The observational practice that leads to these conclusions rests on connecting redshift to distance and time. Redshift can be translated into a look-back time if a cosmological model is adopted and its parameters are measured. The cosmic microwave background, the abundance of light elements, the distribution of galaxies and supernova measurements collectively constrain these parameters. Within the present region, the narrative remains primarily with the concept of horizons, but it acknowledges that this concept is not based on one observation alone. It is the result of a consistent framework built from multiple kinds of data. The observable universe's edge corresponds not to a sharp line of objects, but to a gradual thinning of what can be seen in electromagnetic radiation, because at sufficiently high redshift, the universe was hot and dense, and the light emitted then is stretched into microwave wavelengths. As one looks farther back in time, there is a point beyond which the universe is opaque to ordinary light, because matter is ionized and photons scatter frequently. The earliest light that can be observed directly in electromagnetic form is the cosmic microwave background, which is the afterglow from the time when the universe cooled enough for electrons and protons to combine into neutral atoms, allowing photons to travel freely. That moment sets a practical observational boundary for light in the visible and infrared bands. It means that even within the observable universe, there is a limit to how far back one can see using conventional light from stars and galaxies, because stars and galaxies had not formed yet, and the universe was not transparent. This boundary belongs to the next section in detail, but here it is introduced as part of the horizon concept. There are limits not only in space, but in the transparency of the early universe. In practical terms, the horizon concept also clarifies why distant galaxies appear small and faint, and why their light is redshifted into infrared and microwave bands. A telescope that sees farther must be sensitive to longer wavelengths because the light from the far universe is stretched. It must also collect more light because distant objects appear dim. Yet no increase in telescope power can reveal light that has not had time to arrive, or light that was not able to travel freely before the universe became transparent. The limits are built into the structure of space-time and the history of cosmic plasma. This is where the phrase "too vast" gains its most literal meaning. Not only is the universe large beyond practical travel, it also contains regions beyond observation and beyond causal influence. The maximum region that can be described by direct evidence is finite. Beyond it may lie more universe, perhaps much more. but its details cannot be known by direct observation from here, at least not with any method that relies on signals constrained by the speed of light. This is not an argument about what exists. It is a statement about what can be observed. The narrative remains careful. It states what is constrained by data and physics and avoids claims about unobservable regions. It says only that the observable universe is limited and that this limit is a consequence of finite light speed and cosmic history. Within the observable region, look-back time becomes a way to order cosmic layers. Nearby objects are seen close to the present. More distant objects are seen farther in the past. At very great distances, one looks into the early stages of galaxy formation and beyond that to the time before stars. The horizon thus turns the sky into a time sequence. The farther outward the observation goes, the earlier the universe appears. This is an extension of the earlier local idea that starlight is delayed by years. It is now extended to billions of years. The scale grows until the difference between now and then becomes the dominant aspect of observation. The observer is placed at the center of the observable sphere, not because of special status, but because observation is always centered on the observer's location. Any observer anywhere would see an observable universe centered on themselves, limited by their past light cone. This is a geometric fact of spacetime. It does not imply a central position in the universe as a whole. It simply defines what can be known from a point. In this 11th section, the outer region is therefore the boundary of information itself. Expansion and finite light speed set horizons. The observable universe is finite and shaped by expansion history. Different distance definitions clarify how far sources are now versus how long their light has traveled. Acceleration implies an event horizon in the standard model limiting future contact. The early universe's opacity sets a practical electromagnetic boundary. The calm, neutral conclusion is that the realization of vastness reaches a final form here. There are limits that cannot be overcome by better travel or better instruments, because they are not technological limits. They are constraints on what signals can reach a given place in the universe. The next step inward will be to describe the earliest light that does reach us, the background that fills all directions, and what it reveals about the young universe within the observable boundary. The outer region now becomes a faint, nearly uniform light that fills all directions and does not belong to any single star, galaxy, or cloud. It is detected not as visible glow, but as microwave radiation, a low-energy form of light with long wavelengths. Its existence is established when radio instruments designed for other purposes register a persistent background signal that does not disappear with changes in pointing direction, season, or time of day. After careful checks for terrestrial interference and for known astrophysical radio sources, the signal remains. It is not localized. It is present across the sky. Its spectrum, the way its intensity varies with wavelength, matches that of thermal radiation from a body at a temperature of a few degrees above absolute zero. This match is crucial because it identifies the background as the cooled remnant of a much hotter early state. The radiation is called the cosmic microwave background, and it becomes one of the most direct observational links to the young universe. In the framework where the universe expands from a dense, hot beginning, the early universe is filled with a hot plasma, a mixture of free electrons and atomic nuclei. In this plasma, light does not travel freely over long distances because photons scatter frequently off free electrons. The universe at this stage is opaque, not because it is dark, but because light cannot move straight for long before being deflected. As expansion proceeds, the universe cools. Temperature falls as space expands because the energy of radiation is diluted and because wavelengths are stretched. Eventually, the temperature becomes low enough that electrons can combine with nuclei to form neutral atoms, mainly hydrogen and helium. Once electrons are bound into atoms, the dominant scattering process drops sharply, and photons can travel much farther without being deflected. The universe becomes transparent. The light that last scatters at this transition, then streams outward in all directions. Over billions of years of expansion, that light's wavelengths are stretched, dramatically shifting it from visible and infrared energies down into the microwave range. The cosmic microwave background is this ancient light arriving now as a faint microwave glow from every direction. Its nearly uniform appearance shows that the early universe is remarkably even on large scales, with the same basic temperature everywhere to very high precision. Yet it is not perfectly uniform. When measured carefully, tiny variations are found across the sky at the level of tens of millionths of a degree. These variations are not instrument noise when confirmed by independent measurements and by different observing methods. They are real features. They represent slight differences in density and temperature in the young universe. Those small differences matter because they act as seeds for later structure. Regions that are slightly denser have slightly stronger gravity. Over time, under the pull of gravity, they can attract more matter, growing into the large-scale structures seen later: galaxies, groups, clusters, and the web-like distribution of matter. In this way, the cosmic microwave background does not merely confirm an early hot phase. It also encodes the initial conditions for how structure forms. The outer to inner path continues from the broad presence of the background to the details contained in its pattern. The first layer of detail is its spectrum. The spectrum's close match to a thermal curve indicates that the radiation comes from matter and radiation that were once in near equilibrium as expected in a dense early plasma. This is a strong constraint because it would be difficult for a collection of unrelated sources, such as many distant galaxies, to produce such a precise thermal spectrum. The second layer is the angular pattern of tiny temperature variations. These variations have characteristic sizes on the sky. Their statistical distribution, including the strength of fluctuations at different angular scales, reveals information about the contents and geometry of the universe. A universe with a certain total matter, density, a certain fraction of ordinary matter, and a certain amount of radiation and dark energy produces a distinctive pattern of acoustic peaks, features that arise from sound-like waves in the early plasma. In the hot plasma, gravity pulls matter inward, while radiation pressure pushes outward. This competition sets up oscillations in density and temperature before the universe becomes transparent. When photons decouple and begin free travel, the oscillation pattern is frozen into the radiation field as slight temperature differences. Later, those patterns are observed as the anisotropies in the cosmic microwave background. This explanation stays within known physics gravity pressure and the interaction between light and free electrons. It does not rely on speculation. It is tested by how well the predicted patterns match observations. The cosmic microwave background also carries polarization, a subtle alignment property of light waves. Polarization arises because photons scatter in a way that depends on direction when there are local anisotropies in the radiation field. Measuring this polarization provides additional information about conditions at the time of decoupling and about the later history of the universe, including how matter distribution along the line of sight distorts the pattern through gravitational lensing. The background is thus not a single number. It is a detailed map. Another layer of information is the dipole pattern, a large-scale temperature difference across the sky that is much larger than the tiny primordial variations. This dipole is interpreted primarily as a result of the motion of the observer relative to the rest frame of the cosmic microwave background. Motion toward one direction slightly blue shifts the radiation, making it appear warmer, while motion away slightly redshifts it, making it appear cooler. From this dipole, the velocity of the solar system relative to the cosmic microwave background rest frame can be inferred. This does not establish a special center. It establishes a reference frame defined by the average motion of the early universe's radiation. It provides a practical baseline for describing large-scale motions of galaxies and for separating local motion from the general expansion. In this region, the cosmic microwave background becomes the closest thing to a universal backdrop, not in a philosophical sense, but as a measurable field that fills space. Its uniformity and its tiny ripples set constraints on how the universe behaves at the largest scales. It supports the picture of a universe that begins hot and dense and then expands and cools. It also supports the existence of non-luminous matter. The pattern of fluctuations indicates that ordinary matter alone cannot account for the observed structure growth without conflicting with the smoothness seen in the background. A component that interacts mainly through gravity, dark matter, helps explain how structure can grow while leaving the radiation field as smooth as observed. This is an inference consistent with other evidence from galaxy rotation curves, cluster dynamics, and gravitational lensing. The cosmic microwave background provides an independent line of support by constraining the total matter content and the fraction that is ordinary baryonic matter. The cosmic microwave background also constrains the geometry of space on large scales. The angular size of characteristic features in the background depends on whether space is flat, positively curved, or negatively curved within the cosmological model. Observations indicate that the universe is very close to spatially flat within measurement uncertainty. This does not mean it must be infinite, but it does mean that on the scales probed, the geometry does not show strong curvature. The measured conclusion remains careful. The data are consistent with near-flat geometry, and the precision continues to improve. In addition, the cosmic microwave background helps estimate the age of the universe within the standard cosmological model because the pattern depends on the expansion history and the composition of the universe. By fitting the observed spectrum and anisotropy pattern, cosmologists infer a consistent set of parameters, including an age of around 13 to 14 billion years. The value is not presented here as exact to the last digit, because it depends on model assumptions and measurement uncertainties, but the order and range are well supported. This age connects directly to the horizon concept described earlier. The cosmic microwave background arrives from a time when the universe is only a few 100,000 years old, far earlier than the formation of the first stars. It represents the earliest electromagnetic light that can be observed directly because before that time, the universe is opaque to photons. In this sense, the cosmic microwave background is the practical edge of electromagnetic observation, even though other messengers, such as neutrinos and gravitational waves, could in principle carry information from earlier times with their own detection challenges. The narrative states what is known. The cosmic microwave background is the oldest light that reaches observers freely, and it sets a boundary in time as well as in space. The theme of vastness is refined again. Earlier vastness is expressed as large distances and horizons of observation. Here vastness is also expressed as a universal field that arrives from the entire sky carrying information from a time when the universe is young and the scale of structures is small. The observer sees not a single far object, but the imprint of an early universe on the whole sky. The smallness of the anisotropies relative to the mean indicates that the early universe is highly uniform and that the seeds of later structure are subtle. This supports a calm view of cosmic evolution, small initial differences amplified slowly by gravity over long times. It also underscores the separation between what is directly seen and what must be inferred. The cosmic microwave background is observed as microwaves. The hot early plasma and the transition to transparency are inferred from the physics that connects temperature ionization state and scattering, and from the way the background spectrum and anisotropies match the predictions of that physics. Uncertainty remains in details. The precise nature of dark matter is unknown. The physical explanation for dark energy remains unknown. Measurements of cosmological parameters continue to be refined, and small tensions between different methods remain topics of active research. Yet the core is stable. A pervasive microwave background exists. It has a thermal spectrum. It has tiny anisotropies. It is consistent with an expanding universe that was once hot, dense, and opaque. Within the outer to inner path, this section completes the transition from the limit of observation to the oldest observable light, setting the stage for the next layer inward, which will focus on the large-scale arrangement of matter into filaments, clusters, and voids, and how those structures reflect both the early seeds seen in the cosmic microwave background and the later growth shaped by gravity and expansion. With the cosmic microwave background providing the earliest visible imprint of the young universe and the seeds of later structure, the outer region now becomes the large-scale arrangement of matter in the present-day universe, seen through the distribution of galaxies and the spaces between them. When galaxies are surveyed across large volumes, they are not scattered uniformly like grains in a smooth fog. They form patterns. Galaxies gather in groups. Groups gather in clusters. Clusters link into superclusters. And these larger associations trace filaments and sheets that surround large voids where few galaxies reside. This pattern is often called the cosmic web. It is a description of geometry and density on the largest scales that can be mapped with current observation. The cosmic web is not decorative language. It is a measurable statistical property of galaxy positions. Surveys count galaxies and measure their distances, often using redshift as a proxy for distance under a cosmological model, and calibrating with distance ladder methods where possible. With enough data, a three-dimensional map emerges. In this map, the universe shows a foam-like structure, dense walls and filaments enclosing empty-looking cavities. The emptiness is relative. Even voids contain some matter and some galaxies, but at much lower density than the filaments and clusters. The largest structures are vast, spanning hundreds of millions of light-years. These scales are so large that individual galaxies are small elements within them, and the Milky Way is an almost negligible point. Yet the structures are still finite and describable, and their existence is a direct consequence of gravity acting on the initial small density variations present in the early universe, as seen in the cosmic microwave background. The process layer from early seeds to present structure can be described without embellishment. In the early universe, regions with slightly higher density have slightly stronger gravity. Over time, matter flows toward these overdense regions. In an expanding universe, collapse is not guaranteed. Expansion tends to pull regions apart, while gravity pulls matter together. The outcome depends on the balance between these effects and on the matter content. Dark matter plays a central role because it interacts weakly with radiation and can begin to clump earlier than ordinary matter, which is coupled to radiation in the early plasma. As the universe expands and cools, ordinary matter can fall into the gravitational wells established by dark matter. Gas accumulates, cools, and forms stars, producing galaxies within these wells. Over billions of years, small structures merge to form larger ones. This hierarchical growth, where small halos merge into larger halos, is a key feature of the standard model of structure formation. It predicts that the cosmic web should emerge naturally from the initial conditions measured in the cosmic microwave background. Observations of galaxy clustering, gravitational lensing, and the distribution of intergalactic gas broadly support this picture. The cosmic web is also seen indirectly through the way it affects light. Massive structures bend space-time, causing gravitational lensing. Background galaxies appear slightly distorted when their light passes through the gravitational fields of foreground mass distributions. By measuring these weak distortions statistically across many galaxies, astronomers can map the distribution of mass, including dark matter, which does not emit light. This technique reveals that the mass distribution traces a web-like pattern similar to the galaxy distribution, but not identical, because galaxies are biased tracers. They form preferentially in dense regions. The underlying mass field extends more smoothly. Gravitational lensing therefore provides a way to see the cosmic web in mass rather than in light. Another indirect tracer is the intergalactic medium, the diffuse gas between galaxies. This gas can be detected through absorption lines in the spectra of distant quasars, extremely luminous active galactic nuclei powered by accreting supermassive black holes. As quasar light passes through intergalactic gas, it is absorbed at specific wavelengths, producing a forest of absorption lines that reveal the distribution of hydrogen along the line of sight. The pattern of these lines, called the Lyman alpha forest maps the density fluctuations in the intergalactic medium and provides evidence for a filamentary structure. The intergalactic medium is not empty. It contains a large fraction of the universe's ordinary matter, much of it in ionized form, and it is structured by the same gravitational dynamics that shape galaxies. Clusters of galaxies are among the densest nodes in the cosmic web. A cluster can contain hundreds to thousands of galaxies bound together by gravity, along with hot intracluster gas and a large amount of dark matter. The intracluster gas is heated to tens of millions of degrees Celsius by the deep gravitational potential of the cluster emitting X-rays. X-ray observations reveal the presence and distribution of this gas. The gas can contain more mass than all the stars in the cluster galaxies combined, though dark matter dominates the total mass. Clusters are therefore laboratories for studying matter content and gravitational dynamics on large scales. They also serve as cosmological probes, because the number of clusters as a function of mass and redshift depends on the growth of structure and the expansion history. In this region, the vastness of space is expressed through the scale of the web and the distances between its features. Voids can span tens of millions of light-years. Filaments can stretch for hundreds of millions. The density contrasts are significant, yet the average density of matter is low. Most of the universe's volume is in underdense regions. Most of the mass is concentrated in filaments and clusters. This distribution means that a random point in space is more likely to be in a void than in a filament, even though a random galaxy is more likely to be in a filament. The difference between volume and mass concentration is another way intuition can fail, and it is clarified by the statistics of the cosmic web. The web also has a scale at which the universe becomes homogeneous on average. On small and intermediate scales, clustering is strong. On very large scales, when averaging over sufficiently large volumes, the universe appears roughly uniform with the same average density in all directions. This homogeneity is consistent with the near uniformity of the cosmic microwave background, and with the cosmological principle, the assumption that the universe is isotropic and homogeneous on large scales. The transition scale is not a sharp boundary, but observations support that beyond a few 100 million light-years, the distribution smooths in statistical terms. This matters for the expansion interpretation, because the Hubble law and cosmological models assume that on large scales, the universe can be treated as uniform. The existence of large structures like filaments and voids does not contradict this, because they are still small compared with the size of the observable universe, and because homogeneity refers to averages over large volumes, not to the absence of structure. The cosmic web is also tied to cosmic time. Observations at different redshifts show the web at different stages of growth. In the early universe, galaxies are less evolved and the web is less pronounced. Over time, gravity amplifies density contrasts, making clusters richer and voids emptier. This time, evolution is tested by deep surveys that measure clustering at various redshifts and by simulations that evolve initial conditions consistent with the cosmic microwave background, forward in time. Simulations produce web-like structures similar to those observed with filaments feeding matter into clusters and with galaxies forming at nodes and along filaments. The match is not perfect in every detail, because galaxy formation involves complex baryonic physics, such as gas-cooling star formation and feedback from supernovae and black hole activity. These processes can alter the visible distribution of galaxies even when the underlying dark matter distribution is well understood. In this section, uncertainties are stated plainly. The broad gravitational framework is robust, but the detailed mapping between mass and light depends on astrophysical processes that are still refined. Nevertheless, the existence of the cosmic web is supported by independent methods, galaxy surveys, gravitational lensing, and absorption studies of intergalactic gas. Within this outer region, the theme of vastness becomes architectural. The universe is not a scatter of isolated galaxies in empty space. It is a structured network shaped by gravity and expansion, stretching across distances that dwarf the size of any single galaxy. Yet the pattern also implies limits. Structures do not grow arbitrarily large. Expansion and the finite time available restrict growth. Dark energy, by accelerating expansion, can slow the growth of large-scale structure at late times, making it harder for matter to collapse further on the largest scales. This is an inference within the Standard Model supported by observations of the expansion history and by the evolution of clustering. The cosmic web thus reflects both the early conditions and the later expansion behavior. In this 13th section, the observer's view of vastness is no longer a simple outward ladder of bigger distances. It is a map of connected structures spanning immense volumes where most of space is underdense and where matter is organized into filaments and nodes. The Milky Way is situated within one filamentary environment in this web, and its local group is part of a larger pattern that continues far beyond. The calm conclusion of this region is that the universe's large-scale structure is measurable and consistent with growth from tiny early fluctuations. Yet the scale of that structure and the emptiness between its densest parts confirm that the dominant feature of space on the largest scales is distance itself organized by gravity into a web that extends across the observable universe. The next step inward will be to return to the measurement problem, focusing on how modern methods quantify these vast scales, precisely how different distance measures are cross-checked, and how remaining tensions are handled without speculation. With the cosmic web described as the present-day architecture of matter, the outer region now becomes the precision tools used to measure vastness with increasing reliability, and the disciplined way uncertainty is handled when measurements approach their limits. The basic challenge remains the same as it was with the moon: distance cannot be touched directly, so it must be inferred. What changes is the scale and the need for cross-checks. At solar system scales, radar and orbital dynamics can provide direct distances. At nearby stellar scales, parallax gives geometry-based distances. Beyond that, indirect methods are required, and each method carries assumptions and potential systematic errors. Precision cosmology therefore depends on building multiple independent routes to the same quantity and checking for consistency. One central quantity is the expansion rate at the present epoch, often expressed as the Hubble constant. Its measurement is not a single technique, but a synthesis of a distance scale and a velocity scale. The velocity scale comes from redshift, which can be measured with high precision from spectra. The distance scale must be built from standard candles, standard rulers, or other calibrated indicators. The distance ladder route begins with parallax measurements to nearby stars, which calibrate the luminosities of Cepheid variables and other distance indicators. Cepheids calibrate distances to nearby galaxies. Type 1. A supernovae observed in galaxies with Cepheid distances are then calibrated as standardizable candles, allowing distances to be measured across much larger volumes. This ladder reaches to galaxies far enough that local peculiar motions are less important, and the expansion signal dominates. The resulting expansion rate can be inferred from the slope of distance versus redshift in that regime. This route depends on careful control of systematics. Cepheid measurements require corrections for dust extinction and for differences in chemical composition that can affect the period luminosity relationship. Supernova measurements require correction for light curve shape color and host galaxy effects, as well as control of selection biases that might favor brighter events at larger distances. Each correction is tested by comparing subsamples and by looking for residual trends. The ladder also uses other rungs such as the tip of the red giant branch, which provides a distance indicator based on the maximum brightness of red giant stars before helium ignition in old populations. This method has different sensitivities to dust and stellar population effects than Cepheids, providing a useful cross-check. Another route to vastness is based on standard rulers rather than standard candles. A standard ruler is an object or pattern with a known physical size. If its angular size is measured on the sky, its distance can be inferred. The most important standard ruler in modern cosmology is the Baryon acoustic oscillation scale. In the early universe, sound waves in the plasma create a characteristic preferred separation scale in the distribution of matter. When the universe becomes neutral and photons decouple, this scale is imprinted in the distribution of galaxies and in the cosmic microwave background. It can be measured in galaxy surveys as a slight excess probability of finding pairs of galaxies separated by a particular co-moving distance. Because the physical scale can be calculated from early universe physics, constrained by the cosmic microwave background, it serves as a ruler for measuring distances as a function of redshift. This method is powerful because it relies on large-scale statistical patterns, rather than on the detailed behavior of individual stars or supernovae. It is sensitive to different systematics, such as survey selection, galaxy bias, and modeling of nonlinear structure growth. But these can be tested with simulations and with different tracers of large-scale structure. A third route uses the cosmic microwave background itself. The background's anisotropy pattern encodes information about the composition and geometry of the universe and about the expansion history. By fitting the observed pattern within a cosmological model, parameters, including the Hubble constant, can be inferred. This is not a direct local measurement. It is an inference from early universe conditions, combined with a model that evolves the universe forward to the present. The strength of this route is its precision and the independent physics it uses. The limitation is that it depends on the assumed model. If the model is incomplete, the inferred value could differ from local measurements. This is where the current tension in expansion rate measurements arises. Some analyses of the distance ladder yield a higher present expansion rate than analyses based on the cosmic microwave background, within the standard model. The difference has persisted across improved datasets, making it a significant topic in cosmology. In this section, the narrative treats this tension as an example of how science handles the edge of precision. There are two broad categories of explanation: unrecognized systematic errors in one or both measurement routes, or the possibility that the simple cosmological model needs extension. Both possibilities are actively studied. Systematic errors could include calibration issues in parallax measurements, photometric zero points, dust corrections, or selection effects in supernova samples. On the early universe side, systematics could include modeling assumptions or subtle instrumental effects in cosmic microwave background observations. Model extensions could include changes in the effective number of relativistic species in the early universe, changes in the behavior of dark energy or other physics that alters the expansion history. The narrative does not choose an answer because no consensus resolution exists. It states what is known: both measurement routes are internally consistent and have been refined, and the tension remains. This uncertainty is not a failure of the framework. It is a sign that the field has reached a level of precision where small discrepancies matter and where further measurement and modeling can produce new insight. Precision also involves anchoring measurements to physical constants and to stable reference frames. The speed of light and atomic transition frequencies provide stable standards for time and wavelength. In astrometry missions that measure star positions and parallaxes with high accuracy, provide a geometric foundation for the distance ladder. This improves calibration across many rungs. In addition, gravitational lensing provides a route to distance that depends on geometry and mass distribution rather than on intrinsic luminosity. In strong lensing, a foreground galaxy can produce multiple images of a background quasar or supernova. If the background source varies in brightness, the variations arrive at different times in different images because the light paths have different lengths and pass through different gravitational potentials. Measuring these time delays and modeling the lens mass distribution can yield a distance measure related to the expansion rate. This method has its own systematics, particularly the modeling of lens mass and the environment around the lens, but it offers an independent cross-check. Another emerging method involves gravitational waves. Merging neutron stars and black holes emit gravitational waves, whose amplitude and waveform can provide a direct estimate of distance acting as standard sirens. If an electromagnetic counterpart identifies the host, galaxy redshift can be measured, allowing a distance-redshift relation without reliance on the traditional distance ladder. The method is still developing as detections accumulate, but it provides a fundamentally different route based on general relativity and waveform modeling. In this section, the method is described as a promising independent measurement approach with growing data without claiming precision beyond what current samples support. Across all these methods, the discipline is the same. Each measurement has a statistical uncertainty and a systematic uncertainty. Statistical uncertainty shrinks with more data. Systematic uncertainty requires understanding instruments, environments, and modeling assumptions. Cross-checks between methods help identify systematics because different methods respond differently to the same potential error source. Agreement across methods increases confidence. Disagreement focuses attention on specific parts of the chain. In the context of vastness, the importance of precision is not only to assign a single number to the size or age of the universe, but to make the structure of the cosmic story reliable. Distances underpin the mapping of galaxies, the reconstruction of expansion history, the interpretation of the cosmic microwave background, and the inference of dark matter and dark energy. When distances are refined, the universe's scale becomes more sharply defined, and the remaining uncertainties become more clearly bounded. This is the inner movement within the outer region, from broad measurement concepts to the careful management of error and the use of independent methods. The theme of vastness now includes an additional element as measurements become more precise. Vastness becomes not only large but quantified with small error bars, and the remaining questions become subtle rather than coarse. The universe remains too vast to traverse, but it becomes measurable with increasing fidelity through light geometry and the gravitational behavior of matter and spacetime. This section, therefore, prepares the final inward step, where the story turns from the cosmic scale back toward the practical limits of reach and knowing grounded in the measured constraints and in the unavoidable role of time delays and horizons, concluding the arc from early earthbound measurements to a modern quantified understanding of a universe that is both structured and bounded by what can be observed. The outer region now narrows to the innermost limit that the measured vastness imposes on reach communication and direct knowing, not as an emotional conclusion, but as a set of physical constraints that follow from the properties already described. The progression has moved outward from Earth's shadows to the Moon's distance from the astronomical unit, to stellar parallax from the Milky Way, to external galaxies, and from redshift to expansion and horizons. The inward step at the end is to describe what this scale means for what can be done and what can be observed given known physics. The first constraint is the finite speed of light, which sets a strict upper limit on the speed at which information can travel. Within the solar system, this limit appears as minutes or hours of signal delay. For the nearest stars, it appears as years. For galaxies, it appears as millions of years. No improvement in technology can remove this delay while remaining within known physical law. A telescope receives light that left its source long ago, and any signal sent outward travels forward only at light speed. The consequence is that distant observation is unavoidably historical. Even the nearest star systems are seen with a delay of years, and any interaction with them, if it were possible at all, would involve multi-year waiting for a response. On larger scales, the delay becomes so long that it exceeds the span of civilizations as they are known on Earth. This is not a statement about what civilizations might exist. It is a statement about the timing of signals across distance. The second constraint is the energy required for travel. In Newtonian terms, reaching a high speed requires a large amount of kinetic energy that grows with the square of speed. In relativistic terms, as an object approaches the speed of light, the energy required grows without bound. This means there is a fundamental barrier to reaching light speed with any object that has mass. Even reaching a significant fraction of light speed would require enormous energy and would pose extreme engineering challenges, including propulsion shielding from interstellar dust impacts and long-term reliability. These challenges are not treated here as speculative obstacles, but as consequences of known physics. Interstellar space contains particles and dust grains that at very high relative speeds would carry large kinetic energy and could damage a spacecraft. The medium is thin, but over light-year distances, even a thin medium matters. The third constraint is the scale of distances relative to feasible speeds. The solar system is large but can be crossed in years with high-speed spacecraft, and in decades with slower missions. Interstellar distances measured in light years are thousands of times larger than the scale of the solar system's planetary orbits. At speeds of tens of kilometers per second, which are already high by human standards, a journey of several light years would take many thousands of years. At higher speeds, the time shortens, but the energy cost and technical demands rise. The constraint is therefore not merely that distances are large. It is that the combination of distance, speed limits, and energy makes direct travel to even the nearest stars a project that lies far beyond ordinary timescales. The fourth constraint is the expansion of the universe. On local scales, expansion does not prevent travel because gravitationally bound systems do not expand in the same way as the large-scale metric. A spacecraft traveling to a nearby star or within the Milky Way is not pushed back by cosmic expansion in any practical sense, because local gravitational structures dominate. But on intergalactic scales, expansion does matter for the meaning of distance and for the future accessibility of regions. If expansion accelerates, then over very long times, the event horizon becomes relevant. There exist regions from which light emitted now will never reach an observer here. This is not a practical constraint on travel in the near future, but it is a fundamental constraint on long-term causal contact. The observable universe is finite, and the portion that can ever be influenced or reached even by light may also be finite depending on the future behavior of expansion, as described by the standard cosmological model. This is where the idea of too vast becomes precise. Some regions are not simply far. They are separated by the structure of space-time evolution in such a way that contact is impossible in principle, not only in practice. The fifth constraint concerns the limits of observation imposed by the early universe's opacity. Electromagnetic observation cannot see beyond the surface of last scattering the epoch, when the universe becomes transparent and the cosmic microwave background is released. This means that with ordinary light, no matter how powerful the telescope, the observer cannot see directly into earlier times when photons are trapped in the plasma. Information from earlier epochs might be carried by other messengers, such as neutrinos or gravitational waves, which interact weakly and can travel freely earlier. Yet the detection of such signals is technically challenging and the information is subtle. The constraint here is again physical. The universe's early conditions limit what light can convey. So even within the observable universe, there is a boundary in time for electromagnetic sight. The sixth constraint is interpretive. As distance increases, measurements depend increasingly on models. Parallax is geometric and model light relying mainly on Euclidean geometry at small scales. At cosmological scales, translating redshift into distance and time requires adopting a cosmological model with parameters that are themselves measured. This does not make the measurement arbitrary, but it means that what is meant by distance depends on the chosen definition and model context. Precision cosmology works by comparing independent measurements and by testing model consistency, but some aspects of the far universe remain inference-heavy. Uncertainties in parameters such as the Hubble constant and the nature of dark energy show that even when the broad framework is stable, details can remain unsettled. This is not speculation. It is a feature of working at the edge of measurement where multiple small systematics can matter, and where new physics, if it exists, would appear as a subtle discrepancy rather than as an obvious contradiction. These constraints together define the practical meaning of cosmic scale. They do not imply that the universe is unknowable. They define how it can be known through light that arrives with delay, through signals limited by light speed, through measurements that combine geometry, brightness, and spectral shift, and through statistical mapping of structure. They also define what remains out of reach, direct travel across interstellar and intergalactic space, at will real-time interaction across vast distances and electromagnetic sight into the earliest opaque epochs. The measured vastness, therefore, becomes a set of boundaries around reach and immediacy. At the same time, within those boundaries, observation is rich. The local universe can be mapped in 3 dimensions. The Milky Way's structure can be traced through stars and gas. External galaxies can be catalogued and studied at different times in cosmic history because their light arrives from different look-back times. The cosmic microwave background provides a full sky imprint of the young universe. The cosmic web reveals the large-scale arrangement of matter. These are not vague impressions. They are measured patterns that remain consistent across instruments and methods. The final inward movement is to recognize that the moment humanity realizes space is too vast is not one day on a calendar. It is a gradual accumulation of measurement results that repeatedly expand the scale beyond earlier expectation. First, the moon's distance, then the sun's, then the stars, then the galaxies, then the observable boundary. Each expansion of scale is anchored by a method that can be checked and improved. Vastness becomes real when numbers become stable, and when those numbers imply delays and sizes that cannot be reduced by better travel on Earth or by larger maps. In this final section, the constraints are simply stated. The universe is vast in distance, and that distance converts to time by the speed of light. Energy requirements limit travel to near-light speeds for objects with mass. Expansion and horizons limit causal contact at the largest scales and define a finite observable region. The early universe's opacity limits electromagnetic observation in time. The need for models increases with distance, and precision work continues to refine parameters and resolve tensions. Within these constraints, the universe is still measurable, and the methods that reveal its scale are themselves part of the story: geometry, light, and gravity.